Chapter 8 is probably my favorite in geometry because I love trig. But this is the chapter of right triangles. And this is the chapter in geometry I feel is probably most beneficial to those who are trying to increase their math ACT score. Because there are lots of special right triangles and trig on the ACT. And if you understand this chapter, it should boost your score. It'll also boost your NWEA. Yep. So the first section is really pretty easy and hopefully something you've seen before. And it's just the Pythagorean theorem. Okay, and the Pythagorean theorem applies to any right triangle. And a right triangle just means one of those angles is 90 degrees. Okay, and the Pythagorean theorem is a squared plus b squared, where a and b are the legs of the triangle, is equal to c squared, the hypotenuse is c. Okay, and so we can use the Pythagorean theorem to find a missing side. So if I'm told a and b and I'm trying to find c, I can just plug it into that formula and solve for c. If I'm told a and c and I'm trying to find b, I plug it into the formula and solve for b, and so on. We can also use it to prove whether a triangle is right or not. If we're given all three sides, we can put that into the Pythagorean theorem, and if it's true, if a squared plus b squared does in fact equal c squared, then we know that triangle is a right triangle. So that's the converse of the Pythagorean theorem, when you use it to prove that the triangle's right rather than you're given the triangle's right. Does that make sense? But all in all, you're just using a squared plus b squared equals c squared. Now something in this section that actually comes in really handy is something called a Pythagorean triple. And a Pythagorean triple is just a set of three numbers that makes the Pythagorean theorem true. 3, 4, 5 is the most commonly known Pythagorean triple, because 3 squared is 9, 4 squared is 16, 5 squared is 25. So 3, 4, 5 makes the Pythagorean formula true. Okay, three others that are commonly used are 5, 12, 13, 8, 15, 17, and 7, 24, 25. If you can memorize those, it will help you a lot in this section and on the ACT. The reason is, if I'm given a triangle like this one, and I'm trying to find the missing side, instead of just jumping to the Pythagorean theorem, if you can recognize this is just a multiple of 3, 4, you can figure out this is 15. Right? Because 3 times 3 is 9, 3 times 4 is 12, 3 times 5 would be 15. So the missing side is 15. And you know that because it's the multiple of the 3, 4, 5 Pythagorean triple. That makes sense? If you want to jump to the Pythagorean theorem, that's fine. But when you're on the ACT, as an example, you're allowed 1 minute a question. You want to get through fast. So if you can find tricks like this to get you through faster, knowing those multiples, those Pythagorean triples, will really help you. Because the ACT likes to use all 4 of these. And the same is true here. I mean, if I saw a triangle that was 25, 144, sorry, that's not what I meant, 10, 24, and 26, or I was missing that side, I would know it would be 26, because 13 times 2 is 26, 12 times 2 is 24, 5 times 2 is 10. So if I knew 2 of the sides were 10 and 24, I'd know the third is 26 using that second Pythagorean triple. Does that make sense? Because any multiple of those triples will still be true. 3 times 3, 4, 5, 4 times 3, 4, 5, you can still get to what that side length is using a triple. Okay, and the Pythagorean triples have to be integers. There's an infinite number of them because I can do any order of any factor or product of these. So I could go to infinity with, and there's a lot more than this, but these are the most commonly used for. Okay, so on big ideas, if they happen to ask you, they give you a triangle and it's got 2 missing sides and the third, and they want you to find the third and then answer the question whether it's a Pythagorean triple. If you find the missing side and it's a decimal or it's a radical, it's not going to be a triple because triples always have to be integers. Okay, but you can still find the missing side. Okay, and then the last piece of information, well, not the last piece, I should say. We can use Pythagorean theorem now to find areas of isosceles triangles. Because if you remember, when you draw an altitude from the vertex of an isosceles triangle down to the base, it splits the base into 2 equal parts. And so if I know this base is 16 and I split it into 2 equal parts, I can now use a triple to figure out this is 6, right? 3, 4, 5. Because the altitude's always perpendicular, so it's a right triangle. if I didn't remember that, I could use the Pythagorean formula and find that height. And once I know the height, that's all I need to find the area. I need the base of 16, and now I found the height of 6, and then I divide that by 2 when I multiply them together to find the area of that triangle. Right? So we can use Pythagorean theorem to find the area of isosceles triangles if we're just given the legs and the base and not the height to solve for the height. Does that make sense? Okay, and then finally, another application is to determine whether or not a triangle is acute or obtuse. If a squared plus b squared is less than c squared, it's obtuse. If the biggest side squared is greater than the sum of the two other sides squared, it's obtuse. But if a squared plus b squared is bigger than the biggest side squared, it's acute. So you may have questions on big ideas that asks, looking at the three sides of this triangle, is it acute, obtuse, or right? If it's equal to c squared, it's right. If c squared is bigger, it's obtuse. If c squared is smaller, it's acute. And if you forget, it's in the textbook, which one goes with which. Okay, this is probably the easiest section of this chapter because, number one, it should be a little bit of a review, and it's pretty basic. You're just using a squared plus b squared is equal to c squared for Pythagorean theorem. Okay, so big ideas is open, and so is TK12, if you want to work on that. And then be prepared for section 2 for a textbook check tomorrow morning. Okay?